Okay, welcome to our first lecture. This is Jonathan Templin. I'm the instructor of EPSY 905 in this spring 2018, and this is our first, or at least my first try at having a flipped classroom. So here we go. Today's lecture, this first one, is about descriptive statistics and conceptualizations of variance. The first is something you should be familiar with, probably seen many times. The second is something that we're going to really focus on in this course, so it's kind of a preliminary overview of what's happening. What I'm trying to try to get you to understand from this lecture today is several things. Number one, univariate descriptive statistics. These are things we use to describe a set of data to sort of capture what the information is telling us about a single variable, univariate. So things like where the variable is centered, a mean, a median, maybe a mode, and how much variation there is present. So standard deviation, variance, range, etc. Then we move from one variable to two variables, and so we still have for each variable that same univariate information, but now we can talk about how the two variables are related to each other. This is what we would call bivariate descriptive statistics, and here we would have correlation as a measure you're familiar with, and covariance, which is sort of a distant cousin, or actually more than a cousin, maybe like a step brother or a step sister of correlation. Correlation is something that we pretty much all understand for the most part. But covariance, while it is almost perfectly related to correlation, is something that shows up almost all the time in the multivariate statistics. So we're going to see that and dwell on that a lot today. And then we're going to talk about different types of variable distributions that are out there. These are going to become important to us as we move forward, because each of these has a different understanding. What each of these means has a different interpretation for what you're saying about data. So we're going to talk about marginal distributions. This is like potentially the analog of a univariate descriptive statistic. We can talk about joint distributions, and we can also talk about joint distribution, by the way, is a set of variables together. And finally, we can talk about conditional distributions. So this would be the distribution of y conditional on x. So this sort of gets us into what we do with linear regression or analysis of variance. And finally, we'll hit on bias and estimators. What the heck are both of those terms, and why it matters when we move forward. So, to help understand what we're going to do today, I have a set of R files that are available in a zip folder that you can download. I went ahead and loaded those up into R on my computer here. Make it a little bit bigger for you to see. And the file itself is something that you can just run. You can install the library EPSY 905R, and then you can load the data set already as part of the library itself. And then we can go and assign it a new name. So data 01 is the data that we're going to read in. It has an ID number. There's 20 entries. 10 are supposed to be female people, 10 male. And we have recorded the height and weight of each person, height in inches and weight in pounds. So that'll try to help us see what we're doing as we go along today. The endpoint of the second online lecture will be to build a linear model. This is a linear regression or a linear analysis of variance, or something together with both, that predicts a person's weight based on a person's sex or a person's height. The linear model itself is a definition that we're going to become very familiar with if you're not so already. Linear model is a statistical model for an outcome that uses a linear combination, which is a weighted sum of one or more predictor variables, to produce an estimate of an observation's predicted value. So your linear regression is a linear model. It takes a weighted sum of each of the predictor variables, or the independent variables, weighted by the regression coefficients in front of them, adds them together, and provides a predicted value for an outcome. And what I'm trying to do with this lecture is to get you thinking about how models underlie everything we do in statistics, even if we don't think a model is there in the first place. Everything is relative to some type of model for data, including the descriptive statistics that we talked about previously. So that's our way of thinking that's really going to be enforced in this course as we go forward. So let's first start by visualizing the data, which is a good thing to do. This is a scatter plot matrix that I built in R. You can see the code for it right over here. I can recode males and females into zeros and ones, I can type the pairs statement, and in there you can see the scatter plot matrix itself. These aren't exactly realistic data, but at least it underscores a point of what I'd like to make with this lecture. And the first thing we'd like to talk about is if we just took a look at the histograms of height and weight. Now this would be a marginal variable. This is not conditional on each other. This is not separated by group, female or male. This is just weight across all people and height across all people. You take a look at weight, and sure enough, this thing is bimodal. And you take a look at height, and this thing, not bimodal, but we have a big spike of people in the middle here. It's a little bit skewed. So neither of these look like normal distributions entirely, although height looks a little bit more like that. But what we're supposed to do, what we're going to be doing particularly in the second online lecture, is we're going to be predicting weight. And weight follows this bimodal distribution. Is that something, while you're sitting here thinking, is that something that's allowed for regression? Is this a problem? Are you bothered by this? The hint that I'm going to give you here is that it shouldn't. It shouldn't yet, at least. And I'm going to tell you why as we go through this lecture and the next one as well. So we have these variables, height and weight, essentially. We have equal proportions of males and females, so that's a little less interesting. And we can summarize each variable, height and weight, through a set of descriptive statistics. Each variable what we call marginally, or at the margin. You can think of this as a margin of a table, or I don't know where else you get margin from, but marginal means one variable all by itself. And so there are some common marginal descriptive statistics, such as the mean. What is the mean of height? What is the mean of weight? That's a very frequent one. Median and mode are also out there. The mean is sort of suspect to having outliers really pull it one way or the other, whereas the median and the mode are less suspect to that. The variability is another descriptive statistic. So what is the standard deviation? So what is effectively, you can think of standard deviation as sort of the average distance a unit is away from its mean. The standard amount it deviates from the mean. That's where that term comes from. And then the variance, which is the standard deviation squared, which we up to this point rarely talk about, but it's going to be becoming increasingly popular as we go forward. Popular in the statistics we use, pardon me. Then we can also talk about the range of the variable as well. So those are easy things to pull up with. We can also summarize the joint distribution of the two variables through another set of descriptive statistics. Now, a joint distribution is more than one variable simultaneously. So technically speaking, we could put 4 variables in, or 5, but it becomes harder and harder to talk about 4 and 5 variable statistics. The graph that you saw 2 slides ago, this scatter plot matrix, is sort of a joint distribution of 3 variables. But as you can tell, it's really done by each pair of variables together in a single frame of the graph. That pairing is what we would call a bivariate distribution, or 2 variables together. So anytime you have more than one variable, it's a joint distribution. The one that we most often talk about is a bivariate distribution. A bivariate is a distribution of 2 variables, so therefore it is joint because there's more than one variable in the set. And the common bivariate descriptive statistics that you'll see are correlation and covariance. These things show up quite a bit. So let's go to those real quick. Here are the descriptive statistics for the height and weight data. You can take a look. The average height is 67.9 inches. The average weight is 183.4 pounds. And the average female is 0.05. No, that's just a joke. Terrible one at that. Female is an indicator variable, what we would call a dummy code. So if a person is a female, they will have a 1 for the variable. And if a person is a male, they will have a 0 for the variable. I did that in R in this section of the syntax right above. The standard deviation for height is 7.44. The standard deviation, so that means on average, a person is 7.44 inches away from the mean, or roughly on average, because it depends on what the denominator in the standard deviation happens to be. The weight is 56.383, so it says roughly on average a person would be 56 pounds a little over 56 pounds away from the mean. So you can think of an average person being somewhere in the 230s for weight, or to somewhere down in the 130s for weight, or 120s. And the standard deviation of female of 0.513 is sort of odd because it's a binary variable itself. So we'll get back to that shortly. The variance is the standard deviation squared. So here, standard deviation, we talk about it as the difference, or the average distance a person is from the mean. That the units now become important for each of these terms. What do I mean by units? Standard deviation is expressed in the units of measure of the variable itself. So height is in inches. I mean, standard deviation is also in inches. Variance, however, because it is standard deviation squared, is not in units of inches. It's now units of inches squared. So we rarely refer to it because it is a difficult measure that we think about, because we don't really think of square inches when we go through life. Same thing with weight. Standard deviation of weight is in pounds because we've measured weight in pounds. And the variance of weight is in pounds squared. So those are the univariate statistics at the top. At the bottom here we have the bivariate statistics. This is a covariance or a correlation matrix, and so the bottom triangle of this represents the correlation between each of the variables. So for instance, height and weight are correlated at 0.798. Now remember, correlation ranges between -1 and 1, and there's a reason for that. Once we see the variance, I will mention that just shortly. But so female, the correlation between female and height, this is what we would call a biserial correlation, is -0.593, meaning that as people who are female, the 1 versus the 0 category, are less likely to weigh more. Same thing with, or to be as tall, pardon me. Same thing with weight as well. Down the diagonal of this matrix, I have the variances. Those are the variances that you saw in the column up here. And up the upper diagonal are what we call the covariance. The covariance is a measure that takes that looks at how each term, each variable covaries or is related to each other with units attached. And so what do I mean by that? I'm going to flip the next page forward here. Actually, I'm going to hold off on that. So, for instance, weight is, or the covariance between height and weight is 334.832. But it has units attached to it. We don't really see it just from the numbers here, but we'll see it when we get to the formula for it. What that 334 refers to is the units of height, inches, times the units of weight, pounds. So this is 334 inch-pounds. So that's a little odd. We wouldn't want to talk about that, typically, because it doesn't really have much meaning. The process of changing this covariance to a correlation, though, removes the units from it. So what we have to do is take something with the units of each, in this case inches and pounds, and divide by it to cancel the units out. This is similar to if you've taken a chemistry class. There's a section of that called stoichiometry where you had to end up doing a lot of canceling of units and so forth. This is almost identical in that regard. So here we have weight. The covariance of height and weight of 334.832 inch-pounds. If we divide 334.832 divided by the square root of height, now remember the square root of height's variance, in this case is standard deviation, if we divide by that, now we take something that's inch-pounds in the numerator and divide it by something that's, for height, inches. That would cancel the inches off. And the same thing goes with with weight. If we divide by the standard deviation of weight, standard deviation of weight is in inch-pounds. So really what we're end up doing here is, let me see if I can do a little bit of a better description through mirroring an iPad screen here. All right, so let's think of it this way. The covariance, there we go, covariance is in units of y times units of x, right? And what we want to do to get to a correlation, no units. So what we have to do is take the covariance, take units of y, and divide it by something that would be units of y and times units of x. So let's take a look at this example. Our covariance was 334.832, and that was in inches times pounds. Right? If we take 334.832 and then we divide it by the standard deviation of height, which is 7.44, this is in inches. Inches cancels. And we multiply that standard deviation by the standard deviation of weight, which is 56.383 pounds. And now we get pounds to cancel. So what we end up getting when we take this fraction here is a number, in this case 0.798, that has no units. So that's how it ranges between -1 and 1, always. We've removed any possible unit, regardless of whether our units are in pounds or in kilograms, whether our inches are in, whether our height units are in inches or meters or centimeters or however you want to see it. We've removed each of those from the influence of each variable to summarize it without inches and units, and that's why correlation is such a nice statistic. But that being said, why do we look at covariance? Why do we have to talk about variance? And there's a big reason why. These terms up here in the variance and covariance show up very frequently. In fact, one of the most important distributions that we're going to work with in this class is something called the multivariate normal. It's a joint distribution for more than one variable, where each variable by itself is normally distributed. So each variable marginally by itself follows a normal distribution, but altogether they follow this multivariate normal. The multivariate normal distribution is not expressed with standard deviations and covariance or correlation. It's instead expressed in variances and covariance. It's a little bit more complicated. Of course it is, right? That's how it works, unfortunately. So we're going to focus on this a lot because a lot of our statistics, a lot of our multivariate statistics, a lot of our advanced univariate statistics dwell on variances, and they dwell on covariances. So we have to get a good mindset of that. The other thing I wanted to mention, if you're thinking about covariance, is think of it this way. The correlation, because it does not have units, or because its units are all 1, you can think of a correlation as a covariance between variables with a standard deviation of 1. So both univariate or marginal variables have a standard deviation of 1. The correlation then becomes the covariance between the two. So it's another way of thinking about it in kind of different ways. Okay, moving on. So let's re-examine the concept of variance for just a second. Here we're going to get into, again, in multivariate statistics, our variance and our covariance is sort of a central concept. Here are two formulas for the variance that you may have seen. Usually you may see these, in your introductory statistics class, probably with something to do with the standard deviation. The standard deviation, again, is the square root of each of these. And when we calculate the standard deviation, we typically take the sum across all people of the observation minus the mean squared. And then we do something to it. We usually divide it by either n or n minus 1. And you may have heard in previous courses, that the dividing by n is a biased estimate, meaning that for a given sample, it's not going to be exactly what the value should be for the variance. Whereas the n minus 1 is something we call unbiased, or sample variance. Well, the reason why I'm bringing this up now is because a lot of statistics as we go forward, we're going to find are going to be in the biased camp. In fact, there's a lot of methods that we'll use, multivariate methods we'll use, where we estimate things with maximum likelihood. And sure enough, this divide by n here is the maximum likelihood estimate of a variance. The same thing happens with the covariance, by the way. We'll see that on a future slide. Whereas n minus 1 is something that you'll see and be very familiar with the sample itself. So what I want to talk about is that in general, for large samples, the difference is very small. between the two. So oftentimes we disregard the fact that ML might be biased, although we do try to worry about it in some ways, but we'll get to that later in class. So the interpretation of the variance I mentioned this in the previous slide, but I'll just repeat it again. The variance describes the spread of a variable in squared units, which come from this discrepancy between a person's actual variable observation and the variable's mean itself, the squared term. So the variance is the average squared distance of an observation from the mean, particularly the variance when you divide by n on the denominator. Okay, so because squared units are difficult to work with, we typically use that standard deviation. And when we take the square root of it, we get units back that are what we understand. So it's no longer inches squared, it's inches, no longer pounds squared, it's pounds. So we like standard deviations better. However, variances show up in most of our distributions. So we're sort of in an odd spot with both of those. More generally, variance and standard deviation are often used in what we do with a lot of statistics. So here, variance in the standard deviation does not just apply to a variable that you can observe, but it could also apply to what we would call a sampling distribution of parameters. So for instance, we could talk about how much a regression slope might vary if we were to repeat our observations over and over and over again through this repeated experimental process. So if we think of it this way, we have 20 people and we do this regression, we get a regression slope for height, let's say, and then we observe another 20 people and we get another regression slope. And we keep doing that process over and over again. We'll now have a distribution of that regression slope. And sure enough, that regression slope will have a variance, that distribution, or a standard deviation. Often that standard deviation that we're talking about is no longer called a standard deviation, but it's called a standard error. You may have heard of this term as standard error of the mean before, and that's still from that same idea. If we were to take 20 people, and let's take the mean of height, and we take a repeated sample of 20 people over and over and over again, and just record the mean, the standard deviation of all those means is what we call the standard error of the mean. And so this is a concept that's at its core what we call a frequentist statistics concept. So as we repeat this over and over and over again, that's the frequentist, the frequency of repeating this observation. What do we expect? How much variation do we expect to see in the parameters that we're interested in this case, the mean? So when you see standard error, just think of it this way. It's another name for standard deviation. Right? So I don't like my font there. Standard error often of the mean is equivalent to standard deviation of the mean in repeated samples. So whenever you see error, that typically relates to the parameters of a model. And whenever you see deviation, that typically refers to the data itself. So it's sort of the distinction. Standard error, because error attached relates to parameters. Standard deviation, because deviations attached, relates to data. So if we were talking about the same thing, we could talk about the variance of the mean. It's the squared standard error of the mean, right, which would be this formula up here squared. So more generally, just think of the concept of variance as being equal to error. You can think of about the standard deviation of the mean as being telling you how far off the mean is for describing your data itself, or how much variation it happens to be in it. Now let's get into correlation here. Correlation, similar to variance, involves a discrepancy of an observation's variable from its means. But now we're going to talk, because this is a summary statistics of two variables. This is the Pearson correlation. What we see here is for variable 1, we can take each person's observation minus its mean, and then instead of squaring that like we do in variance, we're going to multiply this by the deviation of variable 2 from a person's observation to the mean itself. We sum that across all people. We can divide by n or n by n minus 1. The same thing goes. This formula at the top of this, right here, oops, I can't get it to highlight, but everything in the numerator, the big numerator here, is the covariance. Right? This term, n minus 1 over n minus 1 times the sum term, is the covariance between y1 and y2. And then the standard deviations show up at the bottom to remove the units from the covariance as well. And so that's what gives us that negative 1 and 1. So a couple other notes. The Pearson correlation of a binary variable with a continuous variable is sometimes called a point biserial. I think I referred to it as a biserial before, but it's the same formula. It just called a different name. And the Pearson correlation of binary and categorical variables with other binary and categorical variables functions a little bit differently, in that you won't always have a maximum correlation of 1 or a minimum correlation of -1. It will be somewhere less than either of those, towards 0 from either of those. So, you might see a correlation. The maximum correlation you could have is 0.86, and the minimum could be -0.86. So that's why when we get into categorical variables, or if you take a categorical, if you look into measures of association in categorical variables, there's many, many, many measures of these associations, and that's because categorical variables, there's no good one term like we have with continuous variables, Pearson. Okay, more on the correlation coefficient. So this whole time in introductory statistics, you were told, oh, use n-1 when you calculate standard deviation, because using n is a biased estimate. Turns out, though, when you calculate the Pearson correlation is biased as well. It's a biased estimate of what happens. How do you unbias it? Well, you can use this formula right here to get an unbiased estimate, but nobody ever talks about that. Nobody mentions it. So I'm mentioning it here to note that there's sort of this odd way we do things in practical statistics, where sometimes we're really worried about bias, but sometimes we're really not. So in this case, we talked about, variance and standard deviation, we can't have those be biased, but correlation, yeah, we can let it be biased. It's sort of an odd mix to me. So just think of it this way: if you're sometimes we have to use bias statistics. Sometimes that's the only method we can do to develop it. An estimator we can use is going to be biased. And what happens? What's going to? Pardon me. That's not necessarily a bad thing. Anyway, what we're going to do is, that's sort of the foreshadowing of what we get into when we talk about maximum likelihood. Maximum likelihood right now is the dominant paradigm of how we estimate most of our multivariate statistics. When we get further on, we're going to see that there are other paradigms as well, Bayesian and perhaps resampling, and we're going to talk about each of those as well. But maximum likelihood is really where bias starts to show up, because a lot of the ML estimates of variance and covariance are biased. And so covariance, again, is that similar to variance. Now, this is the numerator that you saw in the correlation formula from 2 slides ago. We could take n or n-1 of the numerator as well, but we don't necessarily have to. We can use either of these. Most of the ML statistics give us covariances with 1 over n. Most of the unbiased versions use an n-1 analog. So, once again, the covariance uses the units of the original variables. So the covariance of height and weight is 334 inch-pounds. Also, the covariance of a variable with itself is the variance. So if you think about that, take this term and put it over here. It's the two terms squared. So that's what shows up. So we're going to be spending a lot of time on covariances in this class because it shows up in multivariate analyses, because it goes into multivariate distributions, particularly the multivariate normal. So we will see that in the weeks to come. So just time to get familiar with it. The other note is, whenever you see a covariance, you can always translate it to a correlation, and you probably always should if you're reporting it in a journal article or in presentation or otherwise. So you get to see it one way with covariance, but then you can recreate it as correlation, and I'm going to teach you how to do that as well as we go forward. So finally, one last thing. You'll note, to go from correlation to covariance, we've sort of seen this in the correlation slide, and then I talked about it with the covariance itself. The correlation takes the covariance and divides it by the standard deviation of the first variable times the standard deviation of the second. So covariance is covariance divided by product of standard deviations. So you can always go from covariance to correlation so long as you have the standard deviations, which you typically do. Similarly, you can go from correlation to covariance in the opposite way, right? We could say the covariance is the correlation times the standard deviation of variable 1 and the standard deviation of variable 2. This is effectively, this formula on the bottom is putting the units back onto the correlation, whereas this formula right here is taking the units off of the covariance. Okay, so that was the very first attempt at an online lecture. I hope this went okay. The good news is, if anything I said doesn't make sense, you can always repeat it. You can also go to our course Blackboard page and put anonymous comments into a forum about this, any questions or comments that you might have, and I can address those when we have our next lecture. So thank you for watching, and on to the next one.